Experiment 7, Chemical Reactions. Imagine that we had to get something called chemical reactions at some point, right? After all, chemistry is the study of matter and the changes it undergoes during physical and chemical change. So a reaction lab seems totally appropriate. So you've mixed two compounds together, maybe in the lab, maybe in your kitchen or bathroom or around your house. How can you determine if a reaction has occurred or if it's just a physical change? During a chemical reaction, back to chapter 1.3, one or more reactants is converted into one or more different products. We can also check chapter 4, section 3 for that. The shorthand that we use when we talk about chemical reactions are chemical equations, where we have reactants on the left and we have products on the right, with an arrow going from left to right. Why is it left to right? Because that's the direction that English and German are written in, and that's the language of science, for better or for worse. And English is certainly a very challenging language to learn, but that's the way it goes. Before World War II, most chemistry was done in German, and when they lost the war, then it switched over to English. So for an example here, we have hydrochloric acid in water plus sodium hydroxide in water, producing table salt in water and water itself as a liquid. The equations have to be balanced to comply with the law of conservation of matter, to have the same number of each element on the whole left side of the equation as we have on the entire right side of the equation. In this case, 1H, 2 H's over there, because there's the second H. Cl, Cl. Sodium, sodium. Oxygen, oxygen. No matter is created or destroyed. We have just shuffled bonds around. We've changed how things were connected together. Evidence of reactions can be in a variety of different forms, some of which indicate a chemical reaction, but some of which could also indicate a physical change. Presence of bubbles could be something boiling, or it could be a gas that is produced as a product in a reaction. Formation of a solid, generally speaking, is going to be a good evidence that a reaction has occurred, as long as there wasn't solid to begin with. Change in color can indicate a reaction, could also indicate a change. Some things are thermochromic, where they change color upon changing temperature. And something feeling hot or something feeling cold could indicate a gain or loss of heat through a chemical reaction, but also could just be a dissolution. Sometimes when you mix things with water, they get hot or they get cold without a chemical reaction occurring. So you're not absolutely exclusively evidence of a chemical reaction by the presence of some or all of these changes occurring at once. This is qualitative analysis, not quantitative analysis, because we're not worried about how much stuff is involved in the reaction. We're just concerned with, is something involved in the reaction? So here are some gas-producing reactions. If you are driving hydrogen out of a compound, like this hydrochloric acid, you can end up with hydrogen gas. This is an example of a single replacement, because magnesium takes the place of hydrogen, and hydrogen then comes out. Sometimes you may have hydrogens combining with carbonates as an anion and end up getting carbonic acid. And carbonic acid spontaneously decomposes and or can be produced from water and carbon dioxide. Similarly, if you produce ammonium hydroxide, that can decompose to or be formed from ammonia and water. These single things breaking apart into multiple things are examples of decomposition. If we were going the other way, right to left, two things forming one thing would be a synthesis. These are decomposition reactions. Another type of reaction, and this material will definitely help you out in the lecture, is reactions where oxygen is one of your reactants. So, for example, this is a synthesis/combination reaction that is also a combustion, that we are combusting hydrogen with oxygen and producing water. This is combusting or burning using for energy a sugar with oxygen and producing carbon dioxide and water. This reaction happens in your body. This is iron rusting, combining with oxygen to produce iron 3 oxide, otherwise known as rust. So there are a variety of different combining with oxygen reactions which happen in your body, in the environment, in the air, etc., that are definite types of reactions, but recognizing them in the lab could be a little bit challenging, I suppose, other than the fact that the iron looks very different after it rusts. The sugar looks very different after it combusts or is used for energy by combining it with oxygen. The hydrogen and oxygen definitely look different when they are combined to form water. And of course, this reaction would produce a giant fireball as well. In a double displacement or double replacement reaction, it's kind of like what we saw with the single replacement reaction earlier, but we do halves of both molecules. So we saw this reaction earlier, but I have rewritten water here as HOH instead of H2O. So we take the H cation of HCl with the OH anion of NaOH and make HOH. Very helpful oftentimes to think of water as HOH instead of H2O. I take the Na plus cation and the Cl minus anion of the other component, and I make table salt, sodium chloride. So I've split each compound down the middle and swapped halves. If you were raised in the South like me, this would be a do-si-do if you were square dancing. So energy is often absorbed or released during a reaction. Could be when something was just being dissolved, physical change rather than an actual chemical reaction. But regardless, it can be evidence of a reaction occurring. So we want to feel our reactions carefully, of course, to see if it feels hot, the energy being released from the reaction into your hand, or feels cold, the reaction absorbing heat from your hand. When the reaction feels hot, is releasing energy. That is exo, out in Latin, thermic, heat out in the reaction, versus endo, in heat, reaction where it would feel cold because your hand would be supplying energy to the reaction if you were touching it in a test tube, for example, like you're going to do in this lab. So things to think about as you're writing down your observations in this lab. Be as descriptive as possible. This is one of those life skills that makes chemistry a useful experience for you. Be descriptive. All right? You're describing the guy that just mugged you. Oh, he was tall. Okay. Anything else that you may have noticed about the guy? You want to be descriptive. And it's the same thing when we're looking at our reactions in the lab. If you say something is clear, for example, that means you can see through it, as opposed to cloudy where you can't see through it. But what color is it? Clear doesn't mean colorless. Clear means you can see through it. It could be clear and blue, like the water at Six Flags or one of those amusement parks. So you got to specify both. Is it clear or cloudy, and what color is it? Try to see the difference between the liquid color and the solid color if you can't see through it. Is it a colorless liquid with a blue solid, or is it a blue liquid with a white solid? Could look the same. You just got to look really, really, really closely. Then other things to think about practically. What would happen if you didn't really stir the stuff together? It might not have contacted, the two components may not have contacted each other, and you might not be able to tell if a reaction occurred because you hadn't stirred it. And of course, you need to dispose of all your waste properly. So that's it. This is a very qualitative lab. You're looking at what happens for each of the test tubes when you mix the components together. You're going to carefully feel the test tubes to see if it gets hot or not. And you'll look for color changes. You'll look for bubbles as evidence of reactions occurring. But fundamentally, this lab supports the lecture in that you need to predict the products of the reactions. You'll go over that with your instructor. And you need to balance the equations. and then you can qualitatively describe what happens as you watch each reaction occur.